It's everywhere. It powers our homes, our phones, basically our entire modern world. But have you ever stopped to think, what is electricity, really? Well, today, we're going to peel back the curtain and take a look at this incredible, invisible force that makes everything tick. I mean, think about it. You do it every single day without even thinking. But what's actually going on in that split second when you flip a light switch? What's the real science that brings light into a dark room? Well, that's exactly what we're going to dive into. Okay, so to get our heads around that light switch, we first need to meet the real star of the show, electric current. Seriously, this is the invisible force that's doing all the heavy lifting. So what is this stuff? Well, to put it simply, an electric current is basically just a moving stream of these super tiny particles called electrons. The best way to picture it? Think of a river. But instead of water, it's a massive, massive flow of electrons all rushing in the same direction.
Right, so this river of electrons can't just flow anywhere. It has to move in a continuous loop, right? From the power source, through whatever it's powering, like a light bulb, and then all the way back. And here's the key. If that loop breaks, even for a second, the whole flow just stops. So what gets this river moving to begin with?
It all boils down to a super basic rule of the universe. It's kind of like magnets. You've probably heard this before. Opposites attract, and things that are the same, well, they push each other away. This simple little push and pull is literally the engine that drives the entire flow of electricity. Cool, right? So check this out. Electrons have a negative charge. That means they're constantly being pushed away from the negative end of a battery and at the same time pulled super hard toward the positive end. It's this constant, invisible tug of war that actually creates the current.
Okay, so we've got our stream of electrons ready to go. But they can't just flow all over the place. They need a dedicated path, like a highway just for them. And in the world of electricity, that highway is called a circuit.
And here's the most important part, the real takeaway. That path has to be a complete, totally unbroken loop, no gaps. It has to start at the power source, go all the way around, and end up back at the power source. That special, unbroken path is what we call a circuit. And a basic circuit is actually pretty simple. You only need a few key ingredients. First, you need a power source to give those electrons a push. Think of a battery. Then you need the path itself, which are the wires. You also need a load, which is just the thing you're trying to power, like our light bulb. And finally, you need a controller to control the flow. And that, my friends, is our switch. And this is really the bottom line, the one thing you have to remember. The absolute second there's a break anywhere in that path, everything just grinds to a halt. The electrons stop dead in their tracks. That connection absolutely has to be complete. Which brings us full circle, right back to our original question. That simple little flick of a switch, it's all about controlling that path, making it either complete or broken. It's how we take control of the current. I love this analogy. A switch is basically a drawbridge for electrons. When the switch is open, that means the drawbridge is up. There's a big gap in the road, the electrons can't get across, and the lamp is off. But when you close the switch, you're lowering the drawbridge. The path is now complete, the electrons can zip right across, and boom, the lamp turns on. It's really that simple. So when we look at this diagram, that simple little lever, the switch, is physically closing the gap in the wire. The circuit is now complete. This is your on position. It's basically giving that whole stream of electrons the green light to go, go, go and do its thing. All right, we're almost there. Final piece of the puzzle. We've got the flow, we've got the path, and we have the controller. But does the material of that path matter? Oh yeah, big time. Not all materials are invited to this electron party. You can pretty much sort all materials into two basic groups here. First, you have conductors. Think of copper, like in our wires. These guys are great hosts. They just let electrons flow through them super easily. Then you have insulators, like the plastic or rubber coating around those wires. They're the total opposite. They're super clingy with their electrons and basically block the flow completely. Okay, so let's put what we just learned to the test. I want you to take a look at these two diagrams. One of them shows electrons in a conductor, our electric wire, and the other one shows an insulator. So what do you think? Which one is the wire? A or B? If you said A, you nailed it. In a conductor, see how those electrons are kind of free to roam around between atoms? That's what creates the stream we've been talking about. But look at an insulator, like B. Those electrons are locked down tight.
And that right there is why our wires are made of a conductor like copper, but they're safely coated in an insulator like plastic.
And there you have it, the whole secret behind flipping a light switch. It's not magic, it's just really cool science. It all comes down to creating a complete, unbroken path, a closed circuit, made of the right materials so you can let a controlled stream of electrons flow from a power source all the way to your light bulb.
It's pretty amazing when you really stop and think about it, isn't it? You have billions and billions of electrons, all ready to work together in perfect harmony. But just one tiny little break in the chain, and the whole thing stops. It's kind of a powerful reminder of how critical every single connection really is. Not just in a circuit, but, everywhere. Thanks so much for joining me.